Is there any audio disturbance?
Yes, sir. Audio is fine.
All right, we'll start. So we have already started this new topic that is a part of the third module, that is vibration isolation and transmissibility. All right. So yesterday we discussed some points regarding it. So in the previous section we have identified some of the sources of force vibration. So they are listed as harmonic force, which is when it is directly attached to the mass. You have support excitation, you have rotating imbalance, and you have reciprocating imbalance. Okay. So these vibrations, these are the sources of unbalanced forces. Okay. And vibrations are transferred or transmitted to the foundation. Okay. So this effect is undesirable, and isolation of machine from foundation so that no heavy vibration are transmitted is known as vibration isolation. Okay, so this process of isolating the vibration is called as vibration isolation. Now we will see, we'll do some mathematical modeling in case of vibration isolation, and this will be a derivative of the section which we have uh, studied earlier, and here we will be dealing with cases of heavy machinery. So you have a machine and it is placed on some foundation, right? And this machine is oscillating by an external force applied, and the equation for the external applied force is given as F0 sine omega. Right? Now the machine is separated from the foundation by means of this structure. Okay, this structure is called as isolator. Correct? Now for mathematical modeling, I will just create an equivalent model. Alright, so same 4 steps are going to be followed. If I want to create an equivalent model of this system, it will have a mass at the end, that is the mass of the machine. To this mass, external force F0 sine omega t is attached, that is the mass m, and the isolator provides both the properties which are essential for damping, that is for dissipating the energy, that is spring, stiffness, K, and some damping properties. So the isolator will have both these properties, some stiffness as well as some damping. Right? Now we will draw the, so so this is the basically the math equivalent model. So vibration isolators are placed between the machine and the foundation. Right? Examples of vibration isolators are rubber, felt, cork, or metallic springs. So these are some of the examples of isolation. All right. Now, when we are talking about vibration isolation, we also have to define one more term that is called as force. So we have defined isolation. Now we are also going to define force transmissibility. All right. So force transmissibility is defined as a ratio of force transmitted to the foundation to force impressed upon the system. All right. So that is denoted as Ft by F0, where Ft is the force transmitted to the foundation and F0 is the force impressed upon the system. All right. So now here we have a machine. To this machine, this external force F0 sine omega t is applied, and if you want to create the equivalent model, you have this F0 sine omega t applied to this mass m, and the foundation will have some stiffness and some what do you say, damping property. Okay. So next step after we get this equivalent model is, before we have to derive the Gaussian differential equation. So derive the Gaussian differential equation, I'll construct a free body diagram for this mass. So this will be mass m, and since the mass is moving down with displacement is x, velocity x dot, acceleration x, so you have
Sir,
yes.
sir, I don't know if it's just me, but the screen isn't fully visible. It's showing different marks of your mouse. Could you just reshare the screen because
Just a minute.
Yes, sir. Even I am having the same issue.
Just a minute. Just a minute.
Yes, sir.
How about now?
It's
yes,
fine.
sir,
Fine.
completely visible. Yes.
Now it is fine.
Yes, sir.
Okay. All right. So do I have to recap the things which I have just described, or can I continue with the slide?
Sir, continue.
Yeah, continue.
Okay. All right. So construct the free body diagram. So forces are kx, that is the spring force, and damping force cx. All right. And we have already solved for this kind of system. This is an example of force vibration. And as I have said earlier, this whole topic is a derivative of force vibration. So external applied force is F0 sin omega t. So for establishing governing differential equation, I will use D'Alembert's principle. DAP stands for D'Alembert's principle. So summation F is equal to mx double dot, and downwards is positive, so that therefore I get minus kx minus cx dot plus f0 sine omega t is equal to mx double dot. All right. Or so this is the equation, or I can rearrange the terms and write it in the form mx double dot plus k plus cx dot plus kx is equal to f0 sine omega t. That is our familiar form. All right. So this was the free body diagram for the mass. Now this mass is at this machine having mass m, and it has forcing frequency is omega. All right. So this is the free body diagram for the mass. Similarly, we'll construct the free body diagram for the foundation. So when I construct the free body diagram for the foundation, the forces transmitted to the foundation will be equal and opposite to these forces. So this will be acting in downward direction, and it will magnitude will be kx, equal and opposite, and for cx it will be cx dot, sorry, cx dot, it will be cx dot acting downwards. Okay, so this is the free body diagram of foundation. Okay. Now we have your governing differential equation for the mass. So mx double dot plus cx dot plus kx is equal to f0 sine omega t. So steady state response will be x of t, or just x will be capital X, that is the amplitude, into sine omega t minus phi. Okay, of course neglecting transient component. Right? So transient component we are neglecting, as we have done in earlier cases, as it dies out quickly. Alright. So let's construct the vector diagram as we have done earlier, or it is also called as space diagram, for all the for displacement, velocity and acceleration, and also the external force. So external force is F0. So how to construct that? You have to first construct F0, alright? And F0, is at an angle of omega t from horizontal. And so similarly, we have already derived all these things. So displacement vector, steady state amplitude, steady state displacement is given as x is equal to x omega t minus phi. So this angle will be omega t minus phi. Right. So this angle obviously is going to be phi. Right. So F0 leads displacement vector by phi. Alright. Then displacement vector, the velocity vector will be perpendicular to the displacement vector. I hope you are able to recall all these things which we have discussed earlier. And acceleration vector will be diametrically opposite to the displacement vector. Now using this we will construct we'll mark all the various forces. So, draw an x-axis and y-axis. Any questions you ask immediately. So F0, again draw it parallel to F0. Alright. Then m omega square x diametrically opposite to the acceleration vector c omega x in exactly opposite direction to the velocity vector and spring force kx exactly opposite to the displacement vector. All right. I hope you are able to recall all these things. This is called as spring force, damping force, and inertia force. And this is the excitation force. Okay, now what you have, the space diagram is constructed. Now we'll construct the, any questions so far? Alright, so force diagram, space diagram is constructed. Now from this space diagram, we will construct the force polygon. Okay, so force polygon, you are going to arrange the vectors from, so one vector will be in front of the other vectors. Okay, so that we can get the what do you say, the resultant. Okay, so I have arranged the all the vectors. So starting with f0, then m omega square x followed by c omega x and kx. And since this is in equilibrium, this will be a closed polygon. Okay, so all these vectors are basically parallel to these vectors. All right. Now, in addition to the, so this is the space diagram for, these are all impressed forces. All right. Now, using this, we will construct the space diagram, sorry, the force polygon for the transmitted. So you have your, so that as you have, if you recall the free body diagram, see these are all transmitted forces, and they are equal in magnitude and opposite in direction to the impressed forces. All right. So we are going to construct the vector diagram also in the same manner. So in the, at an angle of omega t minus phi, but in opposite direction will be your kx. So I am constructing a vector parallel to this vector, but in opposite direction. My length of this arrow will remain same. Okay. Now c omega x is downward, so here it will be upwards. All right. So this is the spring force kx, and this is c omega x. Okay. The resultant of these two is the transmitted force Ft. So, and we'll also construct F0, that is this one, as a reference. Alright, so this is your F0, and here this will be the angle phi, and this small angle will be alpha. Alright. So from this diagram you can see the difference between the angles made by Ft and F0 with respect to Kx will be phi minus alpha. So what does that mean? It means that the impressed force will lead the transmitted force by an angle of phi minus alpha. Alright. So let's write the resultant of this. So Ft, force transmitted, Ft will be equal to square root of kx square plus c omega x whole square, and that is equal to x into square root of k square plus c square omega square.
Sir, how F naught makes an angle phi with vertical?
Not vertical. This is the angle. This angle. It is the inside angle. Not.
Okay, sir. Okay.
Alright. So x is equal to ft divided by square root of k square plus c square omega square. So here x is what? Your steady state amplitude of mass, and we have already derived the expression for the steady state amplitude of the mass. So steady state amplitude will be given as x is equal to f0 by k divided by square root of 1 minus r square whole square plus 2 zeta r whole square. Alright. So ft divided by square root of k square plus c square omega square is equal to f0 by k divided by square root of 1 minus r square whole square plus 2 zeta r whole square. Alright, and I can rearrange these terms because I want to find the transmissibility ratio, or that is ft by f0. So transmissibility ratio I can abbreviate it as tr, and that is equal to k square plus c square omega square divided by k, and denominator is 1 minus r square plus whole square plus 2 zeta r whole square, and this I can reduce to the form of square root of 1 plus 2 zeta r whole square, and so my transmissibility ratio tr is square root of 1 plus 2 zeta r whole square divided by 1 minus r square whole square plus 2 zeta r whole square. Okay. So if you recall the earlier equations, this is similar to the equation of support excitation for absolute amplitude ratio. Any questions? All right. Now I already described in the slide, ft lags f0 by this angle. All right, and that angle is how much? That is phi minus alpha. Okay. So ft lags f0 by phi minus alpha. All right. So phase lag is phi minus alpha, and that is equal to tan inverse of 2 zeta r upon 1 minus r square minus tan inverse of 2 zeta r. All right. All right. So we have derived the equations. Now we will see some of the features of this transmissibility ratio versus frequency ratio. Okay, and we'll discuss the features one by one, and then at the end of it we'll draw the graphs. Okay? And then we'll have the quiz on the graph. Okay? So transmissibility ratio will be square root of 1 plus 2 zeta r whole square divided by square root of 1 minus r square whole square plus 2 zeta r whole square. Alright. So suppose if this is equal to 1, alright, and I equate both the sides, 1 plus 2 zeta r whole square is equal to square root of 1 minus r square whole square plus 2 zeta r whole square. Okay, and I take the square, so this becomes 1 plus 2 zeta r whole square plus 1 minus r square whole square plus 2 zeta r whole square. Alright, so 2 zeta r whole square, 2 zeta r cancelled, so this becomes 1 minus r square is equal to 1. Alright, so if I take a square root of this, square root of it, I get 1 minus r square is equal to plus or minus 1, or r square is equal to 0 or root 2. Alright. Okay. So if you see, the equation for transmissibility ratio is 1 plus 2 zeta r whole square and square root of 1 minus r square whole square plus 2 zeta r whole square. Okay. So when r is equal to 0, that is at the beginning, TR will be 1. Alright. So all curves will start from point r is equal to 0 and TR is equal to 1. Alright. So all the curves are going to start from this point, and also if you see, this is equal, we have earlier equated this equal to 1. So all the curves, are going to pass through r is equal to 0 and r is equal to root. Alright, so this is the one of the key important features we have to keep in mind when we construct the graphs. Alright. Now second point, at resonance r is equal to 1. So transmissibility ratio reduces to the form of 1 upon 2 zeta. Alright. So now if I make damping equal to 0, the transmissibility will go to infinity. Okay. So that is an undamped system. Alright. So an undamped system is never desired when you are designing any system, because where the system will eventually pass through the resonance phase, and when it does that, the system is going to vibrate violently. Alright. So you have to always make sure that some damping is always provided. Alright. Okay. Any questions? Before I continue, please make sure you write everything down very copiously and neatly, because there is going to be a quiz at the end of this section. So don't miss anything. If you do not understand anything, ask immediately. Everybody is able to see the screen clearly, right? No issues with that, right?
Yes.
Okay. Now transmissibility ratio is given as 1 plus 2 zeta r whole square divided by square root of 1 minus r square whole square plus 2 zeta r whole square. Okay. So what I'm going to do, I'm going to divide both the numerator and denominator by r square. Okay. So after I divide that, I get in the denominator, just write it here itself, I will get 1 upon r square minus 1 whole square plus 2 zeta r whole square. Alright. All right. Okay. So transmissibility, I can write it as square root of 1 plus 2 zeta r whole square divided by r square upon square root of square root of 1 upon r square minus 1 whole square plus 4 zeta square divided by r square. Okay. Now we'll see the key features using this equation. So when r tends to infinity, transmissibility tends to 0. Okay. So if you are operating at higher frequency ratio, then the transmissibility will be less. You can observe that these kind of phenomena when you are using a machine, as the machine is operating at a very high speed, the machine starts to operate very smoothly. All right. Then you will find that the vibrations of the machines are very less as when the speed is very high. Okay. Now, for r less than root 2, you can see the transmissibility curve. So TR will be always greater than 1. This implies force transmitted will be greater than force impressed always when R is less than root 2. Okay. So you can decrease Ft by increasing zeta. All right. Now for R greater than root 2, you will find that the transmissibility ratio is always less than 1. So this implies Ft is greater than F0 always when R is greater than root 2. So you can decrease the force transmitted increases as the damping increases. Okay. So in this region,
Sir,
low, yes,
sir, in second case, Ft will be less than F0.
Ft,
R for greater.
yes, Ft will be less than Ft. So in this region, low damping is preferred. Alright. In this region, low damping is, that is correct. Ft should be less than F0. I have made that correction. Alright. So these are just the points which we just discussed. Now we have discussed all the points. And now we will construct the curve. Okay. Any questions before we move on? All right. All of you, please make note of all these points. At the end of the section, we have the quiz. All right. So let's now construct the curve for. So this is the third curve you are constructing. Uh, Third set of curve. We constructed for magnification factor, constructed for phase angle versus frequency ratio. We constructed for dimensionless amplitude versus frequency ratio. Now this is for the transmissibility ratio versus frequency ratio. So frequency ratio on x-axis, transmissibility on y-axis, and I am going to mark the two most important points always when. So let me first mark the scale. So 1, 2, 3, and 4. Okay. 4 points I am marking, and then again here 1, 1, then 2, and then 3. 2, and this is your point 3. All right. Now draw a reference line. So this is all transmissibility ratios on y-axis, frequency ratios on x-axis. Draw a horizontal line through TR is equal to 1. All right, so this is an important reference line. You need. Okay. Then for R is equal to 1, draw a vertical line. That corresponds to resonance. Now in all earlier graphs, these were our two reference line, but now for this case, we have derived something. So we'll need one more line. This is somewhere here, so that is root 2. Okay. Now, when R is equal to 1 and zeta is equal to 0, this curve goes to infinity. This is the first reference curve. So when zeta is equal to 0, right? And on the other side, so all curves have to pass through 1 and root 2. All right. So this is the second, and this will go to infinity. So this is for zeta is equal to 0. All right. Now as you start to increase zeta, then you will start to get these peak values. And on the other side, this will be above. Okay, so this is for zeta equal to say 0.125. Right? So this is for zeta equal to 0.1. Okay, so far this is for zeta point 1, 2. All right. Now next curve. Again for a higher value of zeta. So as you can see, from 0 to root 2, frequency ratio is 0 to root 2. As zeta increases, the transmissibility decreases. Okay, but from root 2 onwards, when zeta increases, the transmissibility is in fact increasing. Okay, so from 0 to root 2, you are required to have higher damping. From the root 2 onwards, you require to have a lower damping. Zeta is equal to 0.25. 0.125, this is 0.25, and so on and so forth. All right. Any questions so far? And now when you plot this numerical value, you will observe that the curves are shifting to the left. The peaks of the curves are shifting to the left. we are not going to do any discussion about the peaks, because this is not really the operating zone of our machines. But all machines have to go through this zone. Okay, whenever you start a machine, immediately it will not. The motor is, if it is has a rated speed of 1000 rpm, you cannot start the motor at 1000 rpm. Okay, if you start the motor at 1000 rpm, the motor will burst. If you are starting your ceiling fan, when you switch on the fan, it immediately doesn't start at the maximum speed. The speed is increased in a gradual manner. So each machine will go through the range of speeds. Alright. So if you see this curve, when zeta is equal to 0, as you go on increasing the speed, the transmissibility will go to a very low value. Alright. So ideally you will prefer that the value of zeta is 0, right? But the system, when it is starting, it is also going to go through this frequency ratio of r equal to 1, right? So somewhere in between, it is going to go through this resonance phase. So if you keep the value of zeta as 0, then the machine is going to vibrate at very high amplitude when it comes to resonance. Okay, so it is always preferred to give some amount of damping to the system. All right, is that clear? Any questions? So I'm discussing all the very like key points. All this will be needed for your quiz. Okay. Now we'll identify the various zones when we draw this in this on this for this curves. Okay, so we'll identify various zones when this system is in a particular zone, or so the system is operating in a particular zone. What should be the criteria for controlling, for reducing transmissibility? All right. So first thing we have already discussed, for low or low transmissibility, frequency ratio should be greater than root 2. So as you can see, as you go past root 2, the transmissibility goes on decreasing. All right. So ideally zeta should be close to 0, but system goes through, transmissibility will go to infinity when r is equal to 1. So resonance. Okay. So small amount of, so zeta is always kept greater than 0. Small amount of damping is always provided. All right. So when r is small, next point, when r is small before resonance. Okay. So let's pick a very small region somewhere over here. When r is a very small value and the curves are not starting to like peak out. Okay. So this is not like clearly marked value, but this can be determined by experience based on studying the system. Okay. So when r is small, in such case, when k is high, stiffness is high, natural frequency is going to be high. Okay. So r is omega by omega n. So as omega n is high, then r will be low. All right. So this region is called as spring controlled region. Spring controlled region. Right. Now the region near resonance, okay, the region near, at or near resonance. Okay, so region near as r tends to 1, All right. If and zeta tends to 0, transmissibility tends to infinity. All right. So if you are operating in this region, then this region, then you are controlling the transmissibility using damping, and so this region is called as damping control. All right. Now the last zone for higher values of I, that is generally that will be R greater than root 2, transmissibility tends to 0 as R increases or R tends to infinity, or when will R tends to infinity? When omega n is low. All right. So to make omega natural frequency low, you have to increase the mass. All right. So this region beyond root 2, this is called as the mass controlled region. All right. These are the three regions which we just discussed. Any questions before we go to the quiz? All right, done. Everybody is clear. Okay. Now open up your quiz, and last, I think 15 minutes are remaining for the lecture. So you have till the end of the lecture to complete the
So
quiz.
1 minute.
Open up your quiz and start solving. There are total 19 questions, sorry 17 questions, and you have approximately 15 minutes to solve. Everybody has the quiz form, right?
Yes, sir. Sir, please show the questions.
Okay, okay, just a minute. Are you able to see the questions?
No, sir.
No, sir, you have
You
stopped
close
sharing.
screen sharing, I think.
How about now? Are you able to see?
Yes, sir. Yes, sir.
Oh, all right. So you are till the end of the lecture to complete the quiz. You can take a screenshot because I have to go to the next page also. If you are done with the first page, let me know so that I can share you the remaining questions. All are true and false questions. Everybody done with the first page?
No, sir.
Okay, just those students who are still not done with the first page, please raise your hand in the chat box so that I will get a fair idea. I am also uploading the lecture videos in the class material folder. I hope you are able to get that. Okay, some students have already completed it. So now I will just.
Yes, sir. Show the next question.
I will just show the next page. So the students can like take the screenshot, and then I will maybe return to the first page again. Those who are doing with the solving the second page, all of you take the screenshot, and then I can. If many students are remaining on the first page, I'll put the first page. Those who are done can submit it.
Hello, sir.
Yes.
Sir, is question 13 statements correct as it is saying that over a range of frequency ratio starting from 0 to values greater than root 2 means it is saying all the values, not a set of values.
There are values greater than root 2, right?
No, no, it's
Yes, all
saying
the set.
from
Yes,
0
all.
to values greater than root 2.
Yes,
So
entire set of
0
values.
to infinity it's saying.
Yes.
That we have to take only.
Yes.
Okay.
See, if the statement is wrong, you can't say it is false, na? Yes, all of you submit. Last 2 minutes remaining. All right, last 1 minute remaining. All of you submit your responses. After 10:10, I'm going to close. Then nobody who is remaining to submit will be allowed. All right, it is 10:10. Responses are closed. All right, I'm posting the scores.
Sir, just 1 second. I was about to submit.
It's done.
Sir, just
Time
one
is
second.
done. No second. Time is done. I already posted the scores. All right, the scores are posted. If you have any questions, you can ask, or we'll call it a day. Have a great weekend.
So I had a question regarding yesterday's quiz.
Yes.
Sir, in the yesterday's quiz, in the last question, the answer came out to be 0.0056 and the answer I got was 0.0054. Answer
I
I think
have. I think I have like given marks for 000054. No,
no sir, you haven't given sir.
you just refresh the screen and check it.
Okay, sir.
I think I have given marks for 0054. Let me just open it. Lecture.
Yes sir, yes sir. Yes sir,
Huh?
sorry, sir.
Given, no? Got
Yeah,
it, no?
yeah. Okay.
Okay. All right, then. And, if there is nothing else, I will close the lecture. Thank you. Have a good weekend.
Rechu Nambiar, lower hand.